Well, we've had a whole series of talks this afternoon on hardware offload, and this is the last one, so I'll try and provide a little bit different perspective and hopefully some information that we haven't already been through. So I've been involved in the TC Flower effort since the beginning with the Mellanox guys, and we're implementing that, and then I'm going to add a bit more details to how that works. So firstly, being hardware vendor, we want to motivate the hardware offload. This has already been covered several times this afternoon, but the main benefits are you get more packets per second and you get your CPUs back to do other things. So this is a recent graph of using the OvS with the TC offload as compared to the kernel data path. I'm a kernel guy, so I didn't put the DPTK stuff here, but these numbers are quite nice. So this is the number of packets per second varying with frame size, and this is the same test run, but here it's looking at the throughput, and you can see we can achieve the full 40 gigabyte line rate once the packets get over the very, very small sizes. Okay, so moving on to the software side, I'm a software guy. What kind of, how can we offload and how is it that we arrived at this TC Flower model? So in a sense, the kernel data path is an offload itself. It's offloading the user space. Back in the day, the user space data path was not backed by DPTK and it was kind of slow. So the initial solution was to provide the offload to the kernel. So then perhaps a natural extension to this would be to simply offload directly the OvS data path. So every flow that's added to the data path in the kernel would also be reflected down to the NIC and so on. This was sort of the initial metronome effort. It was not accepted into upstream, but it did work quite nicely. So then after quite some debate over several years with the upstream community, this is the model that we've arrived at, and this is what's upstream. So essentially we've gone from having one data path, which would be the one labeled OvS data path sitting in the kernel. We actually end up with three. So we have the OvS data path still there. We have the TC software data path, and then we have basically the same data path down in the hardware. In practice, the TC data path in software is usually left empty. It's not populated. So in this model, packet comes into the system. If the flow exists in the hardware, it's forwarded directly and never touches, doesn't have to go across the PCI bus and so on. This is best case scenario. If the flow is unknown, then it gets pushed up to the kernel. It's run through the TC data path, but as I mentioned, that's usually empty, so it doesn't do anything. Then it goes to the OvS kernel data path. That may have the flow, because there could have been a decision made to put it into software rather than hardware. It doesn't always make sense to put all flows into hardware. For instance, ARP, you don't expect a very high packet rate there. Maybe it's just as well just to put it into the software. But ultimately, if there's no flow in the OvS data path, it goes up to user space and it decides what to do with it. So what is TC Flower and why is it that we're using it for this application? Okay, so overall, it's pretty similar to OvS. So it's a packet classifier in the Linux kernel. It's part of the TC subsystem. Like OvS, it allows matching on a variety of predefined flow keys. So you can match on, say, IP addresses. You can match on UDP ports. You can also match on metadata and tunnel metadata and so on. It doesn't allow you to do arbitrary matches on, say, specific bytes at specific offsets and so on, but neither does OvS. And then we have the action side. So it's a match action system, also like OvS. Some of the actions have kind of non-intuitive names, but overall the feature set is kind of similar to OvS. We have pedit, which is equivalent to the OvS set action. We have mode, which is basically the output action. We have VLAN action. We don't have some things like MPLS, but these can be added to the framework. So here's an example of writing a TC Flower rule. There's no OVS involved in here. We're just matching on TCP packets to port 80, and we're dropping them. So this, if you squint and sort of use your imagination, this kind of looks similar to an OVS flow. It's just expressed in a different way. So TC Flower can be offloaded, and so we need to have some kind of policy, some kind of controls where the user space, so the user can influence what's offloaded and what's not offloaded. And so firstly, we have this global per interface configuration where you're allowed to basically turn the offload on and off. And then we have finer grained control where on a per flow basis, we can use these skips, hardware and skip software flags to control the placement of individual flows. And the default would, which is when neither of these flags are used, is to try to put it into hardware if the hardware exists and they're willing to accept it. And regardless of what happens there, to put it into software. So if you have offload hardware, you end up with it in both locations. I mentioned earlier that typically in the OVS use case, we don't place the flows in the software, so the skip software flag is used. And then lastly, we have these flags which allow the kernel to report back to user space where exactly the flow was placed. So here's the same example as before, except I've added the skip software. So this means I want it to be placed in hardware. If it can't be placed in hardware, I'm expecting an error. And now I query the system to ask where the flow is, and in bold, we can see that it, firstly, skip software was requested, and secondly, it's been placed in hardware. Okay, so hopefully given a little bit overview of TC Flower. Now, how does this match up with OVS, and how can we use it there? So here's a little bit of comparison of the two different data paths. OVS has a single table in the kernel data path. TC Flower kind of has multi-table now because it has these things called chains, but it can certainly cover the single table case. In the OVS case, we match on the import. In TC Flower case, at least up until now, we actually attach the rule to the import, so it's implicitly matched there. As I mentioned, we can match on a wide variety of flow keys. In the OVS case, the flows are disjoint, and we can kind of partition them. In TC Flower, the flows may or may not be disjoint. It depends what you want to do. In OVS kernel data path, we don't really have a concept of priorities as such. We don't really need to because all the flows are disjoint. In TC Flower, it does allow overlapping flows, and there are priorities. And implementation detail, which may go away at some point, is that we can only have one mask per priority level. So if you want to use multiple masks, which you typically do, you have to put them at different priority levels. Now, if you're taking OVS flows and putting them to TC Flower, the ordering of the priorities is not important as, from a correctness point of view because the flows don't overlap. But if they do overlap, you're in a different use case and they overlap, you have to order them depending on the behavior you want. Okay, so just briefly, this hooks in, we use NetDevOps. NetDev is the vPort layer inside OVS. And these are called by the DPIF layer. So this is after the flows, the OpenFlow flows are translated into data path flows. And it's at this data path flow layer, the DPIF layer, where we attempt to push the flows into hardware if it's enabled. If the flow is successfully added to hardware, then that's good, if that's the end. If it fails to be added to hardware for any reason, so a typical reason would be that the flow is not supported, then it goes to software. So we put it into the kernel data path. So how do we configure this and so on? It's disabled by default, so it's a new feature. Maybe it has a few rough edges on it, so if you out of the box, it's turned off. So firstly, you need to globally enable it using this magic command. And then, like TC Flower itself, it has policy controls. So these aren't actually per flow. It's a global setting, which is then used per flow. So we have the same, the default, the skip software, and the skip hardware. And typically, you would use the skip software mode. Although, if you use the skip hardware mode, then you could use this offload to populate the alternate data path in the kernel without using hardware. So this policy is also set globally. We can view the flows. So if you use the normal flow view command, then you just see all the flows as you would normally, but you don't know where they are, if they're software or hardware. So we can provide a filter on the viewing of the flows. If you ask for the OvS flows, this is the software ones. And if you ask for the OvS offloaded, then this is the ones that are being handled by TC. So the current feature set, what's implemented as of about now, we can match on L2 through L4 fields. I'm sorry, and also tunnel metadata. Sorry, this slide seems to have some duplicate information, but so we can match on L2 through L4 and tunnel metadata. And the actions, as I listed earlier, we can do things like drop and output and VLAN. There are some limitations here. We can only currently output to one port, but this limitation can easily be lifted. So what's the status? As was mentioned by Ronnie a bit earlier, it's all been put upstream, although we're still chasing the feature gap. So as of OvS 2.8, you can enable this feature. The TC Flower stuff was initially added way back in 4.2. It's been progressively, the feature set's been enhanced ever since. And the Metronome NFP driver has been supporting this since 4.13. So future work, I already mentioned the feature gap once or twice. There's plenty. So there's a set action. It says patches available, but actually I merged these the other day, so they're upstream too. Then there's kind of edge case things like IP label and neighbor discovery. Maybe you want to offload these, maybe you don't, but from my point of view, it would be nice to at least support these in the software TC implementation. There's some trivial things that are missing, like we can match on MPLS, but only exact match. There's things like Geneva options. OvS allows you to match on Geneva options and set them. It would be nice to support that, and that would be applicable to other use cases. And then there's kind of bigger picture items like metering and QoS. Bonding falls into this category as well. And then there's contract. I'll spend a moment or two speaking about this. My colleague John covered it well yesterday, but by using contract, we can write better security policies than we can with a purely stateless system. OvS has had this for a while now. It would be very nice if we could connect together the contract support that exists in the kernel with the TC Flower. And the proposal that's been put forward is essentially to follow the same model as OvS, which is you have a contract action, which passes the packet through the contract subsystem and then returns some metadata, which you can match on. So you have a first match action pass, which does an initial classification of the packets, passes it to contract, and then a second match, which would match on the metadata fields filled in by contract. Okay, thank you very much for your time. I do have one more slide, which is we have an event coming up, and if you're interested, please register. Thank you very much.
All right, we have time for questions. let's see. It looks like nobody's popped up quite yet, so I'm going to ask my own question then.
Sure.
So I know that Metronome has had at least one previous generation of acceleration for for Open vSwitch that used probably more custom-written hooks that I doubt ever got upstreamed.
That's right.
So my question is, how satisfactory is the TC Flower-based acceleration from a Metronome point of view, I don't know, completeness, performance, et cetera, compared to what was available before?
Yeah, so the previous model, which was to hook in directly to OVS data path, which was significantly easier for us. But one of the big drawbacks, not so much for us, but for other people, is if you couldn't offload certain flows, it was very difficult to control. So this approach that's been taken by the community is a bit better for everyone. Not necessarily better for Metronome, but better overall.
All right, that's good to hear. Justin, go ahead.
Yeah, I was just curious, how does tunneling work in this situation? So like TC Flower, I assume, is usually executing after the Linux kernel has had a chance to do like IP processing. But how does that work with like the hardware offloads then? Is it assumed that they're doing that? Or
Yeah, so with TC Flower, you could either filter on the encapsulated packet coming in off the wire or the unencapsulated packet. It's usually the second case that you do. This does provide some challenges for offloading, but essentially what we do is, I guess the difficult part is you have to offload part of the neighbor table down into the NIC, and you have to make sure that that's kept. If the neighbor table changes for any reason, you have to propagate the updates. And you also have to propagate liveness from the card up to the host, so the neighbor table entries don't expire. Yeah, it's kind of difficult to explain all the details without some slides.
Yeah, no, that makes sense. And so, but then you have like the enable or like no software flag, I can't remember what it was called.
Yes.
And so if you wanted to offload some sort of tunnel processing, then would it be expected that the NIC, if it wasn't maintaining all of those tables, that it would say that it doesn't support offloading tunnels, for example?
I'm not sure I understood the question, but if you request TC to offload something and then it's pushing it, then it makes a call into the driver, and the driver should know what the hardware can support, and at that point it can reject the flow if it's, for whatever reason, if it's not supported, if it's tunneling protocol it doesn't understand.
Yeah, I meant more in terms, is it the expectation that if the hardware wasn't updating things like the neighbor, retrieving the neighbor information and updating it, would it be expected that it would say that it doesn't support tunnel offloads, for example?
Yeah, I mean, it's a little bit it's really up to the driver to decide, but yeah, if you're not offloading the neighbor table, I think you should reject it.
Right. And do you know if like I think the big supporters right now are Metronome and Mellanox. Do you know if, like, does Metronome support the tunnel, for example?
So I won't speak for other vendors, but Metronome does.
Okay,
yes.
Great, thanks.
So can TC offload be handled by normal Metronome NIC?
So normal Metronome NIC would be a smart NIC. So yes, it's supported.
Another question is, because many companies are using OvS DBDK, so can you offload TC to Metronome NIC in OvS DBDK?
So currently, there are several answers to that question. Yes, it's possible. No, it's not implemented right now. I would think that the way that the upstream proposal for DBTK offload works is slightly different. This is the partial offload that was being talked about in other sessions. And then the session a bit earlier talking about how to extend that to full offload. It seems to be the approach that's being preferred by the DBTK people, but certainly it would be possible to do some kind of translation or something using TC Flower, and that might, it's better reuse in a way. But then on the other hand, you're essentially taking something that's been designed for the kernel and then using that as the basis of your API for user space. So whether or not that makes sense, I think is an open question.
Anybody else? All right, let's thank our speaker.
Thank you very much.